Alright, today we're going to be looking at section 3.3, rules of differentiation, and these will be just some shortcuts to find the derivative instead of doing the difference quotient and taking the limit as we go to 0. So the first one is a constant rule that we are given. You're going to see this notation d dx, that means find the derivative, and if we're taking the derivative of a constant, it's just going to be equal to 0. Then theorem 3.3, we have the power rule. This is if n is non-negative, which means it's positive, or even if you have a 0. The derivative is going to be given by taking that power, multiplying it to the front, and then subtracting 1 from that exponent. And so they're showing you the proof of how that works, and that you end up with the same thing. Again, you have the constant multiple. So if you are multiplying a constant time a function, you can just pull that constant out and then find the derivative of that function and then multiply that constant at the end. Then you see some examples of that in use. You have the sum rule, which is just saying if you are finding the derivative of a sum, that is equal to the sum of the derivatives. And then here's some proof of that, going through that using the limit definition. And then just generalized sum rule, it doesn't matter how many functions you have. If you're adding them up, you can just take the derivative of each of them individually, and then that would be the same as adding up all those derivatives at the end. Same thing will apply with difference. Okay, you can find the derivative of a difference by taking the difference of the derivatives. And then here's just an example, which we'll do these in my math lab after we go through this. But read over these examples, you can kind of see how they're using them. And then we do derivative of natural exponential function. There's the proof of it. The short of it is if you want to take the derivative of e to some power, it's just going to be e to that power. And this is just a natural exponent where you don't have some constant or multiple up there. And again, here is the proof of how that works. And then here it is them just giving you derivative of e to the x. For all real numbers, x is just going to be e to the x. And then when it says finding tangent lines, once you find the derivative, okay, the derivative is going to give you the slope of that tangent line. And then you plug in whatever point you're given, and you can find the equation of the tangent line. It is important to know that the tangent line, the slope is going to be 0 at a maximum or minimum point. That's going to give you a horizontal tangent line. So here they're just kind of going over the slope of the tangent lines, and you get different ones. And then higher order derivatives. So this notation, f prime is a first derivative, f double prime is second, and then triple prime is a third derivative. And so anything where n is greater than 2, so you're trying to find the derivative, second, third, or greater, those are called higher order derivatives. And then here is just different notation that they're showing you. F double prime is just finding the derivative of f prime of x. And then again, you can write that for any n greater than 1. And then you also have some other notations. You got this d2f over dx squared. And it's just saying this comes from the d dx form. They just multiply that times the derivative of f with respect to x. And you get some different forms. So these are also just showing you different ways of writing derivative or higher order derivatives. Okay. And with that, that'll cut off the overview. we're going to jump over to my math lab and solve a few problems.